In this lecture, we will go over the CFA Level 2 reading on time series analysis. For many people, quantitative methods at Level 2 is somewhat difficult, and within quantitative methods, as you know, we have 3 readings. This is the third and final reading, and arguably one of the hardest, because it takes on the concepts that we've discussed before and adds more to those concepts. So try to absorb this material. From a testability perspective, I'd also say that this is high probability, because as an examiner, if I want to test your concepts across all that we have studied in quant, then I will go for this reading, because this covers regression and then it adds the time series component. Time series in finance and economics is very important. A lot of data that we consider is time series data. If you look at stock market data or stock data, inflation data, interest rate data, all this is time series. So that's why time series analysis is extremely important. There are several sections in this reading. Not all these sections are emphasized in the learning objectives. So I will follow the sequence in the curriculum and make it flow well, but I'll spend more time on topics which are emphasized in the learning objectives and the examples and the practice problems. And I'll spend less time on sections which are not emphasized in the curriculum. Let's start with section 1, a basic introduction to time series analysis. You probably know this already, but here is a formal definition of a time series. A time series is a set of observations on a variable's outcomes in different time periods. So you take a given variable such as monthly US retail sales over a given time period, plot it out or look at the data. That is one example of time series data. Why do we use time series data? There are several uses, but the 2 primary uses of a time series model are shown right here. You try to explain the past, and more importantly, I'd say you try to predict the future of the time series, because ultimately in finance, you want to try and predict what will happen. And how do you predict what will happen? By understanding the past and then using that logic to try and predict what will happen in the future. Okay, what are the major challenges of working with time series data? This is also a very brief section in the curriculum. Working with time series, we often find that the assumptions of linear regression model are not satisfied. When those assumptions are not satisfied, in many cases we can transform the time series or specify the regression model differently so that assumptions of the linear regression are met. As you might imagine, there will be a lot of transformations that take place in this particular reading. The specific problems dealing with time series include the following. The residual errors are correlated instead of being uncorrelated. And the reason is that time series data is often cyclic. And whenever you have cyclic data, the probability of errors being correlated is higher. So this is something that we are going to look out for. The mean or variance of the time series changes over time. In other words, the data is often not covariance stationary. The other point is that the mean or variance of the time changes over time, which means that the data is not stationary. And we'll talk a lot about both of these items. Section 3 deals with trend models, and section 3 in the curriculum has 3 subsections. We'll first talk about the most basic kind of model, which is a linear trend model. Then we will talk about log linear trend models, because if you look at something like sales growth is generally exponential over time. So we'll see that a simple trend model or a linear model will not work. So we'll need some transformation. And with exponential data, the transformation involves logs. And then we will look at trend models and testing for correlated errors. As we've discussed with time series data, the big issue often is that errors are correlated. Sometimes it will be obvious that the errors are correlated, but if it is not obvious, then you need to do certain tests. And we'll talk about those tests. Okay, so section 3.1, the most basic model we'll talk about in this lecture, which is a linear trend model. The definition. With a linear trend model, the dependent variable changes at a constant rate with time. So the independent variable is time. When we plot this out, the independent variable or the x variable is t or time. And you have some dependent variable, whatever that might be. It might be sales data, it might be some other variable, but we are plotting a best fit line that connects time with our dependent variable. And this is the form of the equation. Does this look like single variable regression? It does. The only difference is that instead of x, we are using t. And then we come up with an equation in the form y is equal to mx plus c. So the idea is fairly straightforward. How will you use this model to predict a value for y? You plug in t and come up with the value of y. As before, the expected value of the error term is 0. Let's look at example 1, which is the simplest example that we'll cover today. The trend in the US Consumer Price Index. So we are looking at inflation numbers. As you can see, you have time on the x-axis and inflation or CPI on the y-axis. This is the data. We run a regression and we get this regression output. So there are some things to note over here. The first is that we have a very low R squared. Does this surprise you? It should not, because as you can see over here, even if you get a best fit regression line, something like this, slightly sloping down maybe, and how do I know it's slightly sloping down? Because this trend coefficient is very slightly negative. It's not 0, it's slightly negative with a significant T star. So there is a clear downward trend. And notice this is called the trend because in other cases we call this B1 or the slope coefficient. Here the slope is the trend. Okay, what does this mean? This means that the amount explained by the model is only 4.8%. So it explains a small amount. It's not useless. It's not extremely useful either, but keep that in mind. Okay, so now what is the equation that we write down based on this output? That equation will be that the dependent variable at time t is equal to the intercept, which is 4.13. I'm just taking 2 decimal places. Actually, I should take more than 2 decimal places given this number. So I'll take the full thing, 4.1342 minus 0.0095 times t. And then there is an error term with an expected value of 0, which means that we can simply plug in values of t and get a prediction for y. Just to get you to do a little bit of work, I want you to tell me the predicted value of y when t is equal to 192. Here is what you should get. And keep in mind that at the end of almost every regression exercise, there will be a question which says, here is the x value, or here is the independent variable value. What is the dependent variable? In this particular case, with t equal to 192, you should get approximately 2.3177. We now move to the next section, which is log linear trend models. Sometimes a linear trend does not correctly model the growth of a time series. If you consider example 2 in the curriculum, which is looking at Intel's quarterly sales data between 1985 and 2000, this is what you have. So this data over here is the actual. It looks like this data is growing somewhat exponentially. Obviously not a perfect exponential function, but simplistically it looks exponential. And the dotted line is the best fit regression line. If we take the data, use a simple linear model, in other words, we don't do any transformations, then this is what we get. All right. On the surface, it seems like the t-stats are significant. It seems like R squared is decent. But when you look at this data, there is clearly a correlation between the error terms. I have not shown it here, but in the curriculum, they actually plot out the error terms. When you know this error term at time period, say 92, can you predict that the next error term is also going to be somewhat similar? So is there a autocorrelation issue? This is clearly an autocorrelation issue. Has a regression assumption been violated? It has. So is this model properly specified? No. So we need to do something else. What do we do? When we see something exponential, then we should use a log linear model. And in general, log linear trends work well in fitting time series that have exponential growth. Specifically, here is the little bit of mathematics that you need to do. So what is our dependent variable? That dependent variable y is the sales, and take this as a given. So the sales then, when you have exponential growth, can be best expressed like this: e to the power of b naught plus b1 times t. This is mathematics, and just take this as a given. Now, if you have a relationship like this, what do you do? Again, some basic mathematics. You take the natural log of both sides. When you take the natural log of both sides, what does this become? You have the natural log of y at time t is equal to what? Again, this is basic mathematics. When you have ln e to the power of something, this something, the exponent actually comes down here. So you have b naught plus b1 times t multiplied by the natural log of e. Natural log means base e, so base e, and you have e over here, that is just 1. And you are left with this relationship. So what does this relationship say? It says that the natural log of the sales number in a given period is given by this. Alright, now we move on to example 3, which actually uses the fact that we just talked about. We will now consider a log linear regression for quarterly sales at Intel. Have we re-specified our model? We have. So this is the new specification. What does y stand for? Y is sales. So ln y is the natural log of sales at time t. And we have b naught. What is the independent variable? It is simply time. All right. So we run this regression. T is 30. And we get this output. Notice that the R squared has improved. It was high before, but it is even higher now. And the t-stats have actually also improved. Now, it looks like the error terms are not really as correlated over here. Later on, we'll do more formal tests, but things look much better with this model. So assuming this is true, and for now we will assume that this is good, here is what I want you to do. At t is equal to 61, what is the predicted value of the sales? Use the data given, the regression statistics given, and come up with this answer. Here is what you need to do. Recognize that this is the form of the equation. The natural log of y at time 61 is equal to 5.5529. Where is this coming from? This is the coefficient, plus this is the trend value, which is coming from here, and this is the t value, or the time value, which is given. This expression is simple mathematics. When you do this, you should come up with 9.2673. And then using basic mathematics, y at time 61 is e to the power of this number, 9.2673. And on your calculator, you should be able to do this. The answer should be 5.63 million. So this is the answer. And get used to this. As I keep saying, it is a guaranteed question on the exam where you'll be given the x value or the independent variable and you need to find the dependent variable. The next section is brief but important from a testability perspective. Trend models and testing for correlated errors. As we've said several times, whenever you do a regression, be it a time series or a basic trend model, the way we've set it up, the regression model assumptions must be satisfied. If they are not satisfied, then we have an issue. The most common sort of issue that we have with trend models is that there is a correlation between error terms. If you have a situation where this issue is not obvious, then what do? You do the Durbin-Watson test. And we learned about the Durbin-Watson test in the previous reading. The details of the Durbin-Watson test are in the appendix. And I'm going to emphasize Durbin-Watson test over here because the first question in the curriculum, in the practice problems, actually tests you on Durbin-Watson. So I'll give you the very simplistic, quick version of the Durbin-Watson test. The Durbin-Watson stat ranges between 0 and 4. And this middle value or hypothesized value is 2. If you calculate your Durbin-Watson stat, and the previous lecture covers how to do that, and your Durbin-Watson stat is somewhere around 2, then you don't have a problem. If the Durbin-Watson stat is far away from 2, more towards the left, something like say 1, then you have a problem. This would imply that there is probably a positive correlation between the error terms. And if your Durbin-Watson stat is closer to 4, to the right of 2, then you probably have a negative correlation between the error terms. So keep that in mind. And again, if you're not sure, then listen to the lectures associated with the previous reading. Okay, now what do you do if you have a trend model and despite your transformations, you still have this problem? Then you need to move to a more sophisticated model. The most sophisticated model is an autoregressive time series model, also called an AR time series model, or just an AR model. What's the definition? An autoregressive model is a time series where a given variable is regressed on its own past values. So simplistically now, if we think about what we've studied in quant, we have talked about 3 kinds of regressions. The first kind of regression was where you have a given dependent variable which depends on another independent variable, and then we might just add to this and say we can have multiple independent variables. Then we got to the next level and said that we can have a trend model where y depends on time. Now with autoregression, we are saying that a variable depends on past versions of itself. So it doesn't make sense to have x and y. It doesn't make sense to have y and t. Now we just have one variable. So what we'll now have is just an x variable, which depends on a previous version of it. So you will notice the subscript t stands for x at time t, and obviously t minus 1 stands for the value of x at time t minus 1, and then the coefficients b0 and b1 quantify that relationship between the dependent variable and a previous version of that dependent variable. Your simplest kind of AR model is an AR1 model. The 1 just means that you are regressing against one lag. Taking this one level further, or in this case we can say taking it one level back into the past, we can have an AR2 model. So XT now depends on the previous version and the version before that. So this is AR2. Hopefully you can figure out what we mean by a AR3 model or an AR4 model. Why do you think an AR4 model might be important. The reason is because of seasonality that we'll talk about later. For many companies, sales are seasonal. So it might be important to understand the sales 4 quarters ago, right? Or in some cases, the seasonality is down to a monthly level. There, what sort of a model will you have? An AR12 model, right? But in general, this is what we say. An ARP model means that we are going back up to P lags. It doesn't necessarily mean that you have 1 lag, 2 lag, 3 lag, 4 lag, all the way to P, because some of these coefficients in the middle might be 0. So you might have a X that depends on 1 lag earlier and 4 lags earlier. That would still have P equal to 4. The way you can think about it then is the B2 and B3 in that scenario are 0. What I've done here is listed all the subsections in this particular section 4, and I would say that this is one of the most important sections in the reading. It's also one of the longest. Section 4.1 deals with this concept of covariance stationary series. Then we will talk about detecting serially correlated errors in an autoregressive model. Just because we moved to an autoregressive model doesn't mean that we've solved the problem of error terms being correlated. So we need to figure out whether the error terms are correlated or not. If they are not correlated, great. If they are correlated, then what do we do? Then we talk about this concept of mean reversion, which is extremely important. By and large, in section 4, we assume that our data is mean reverting. In the section after this, then we look at what to do when the data is not mean reverting. Multi-period forecasts and the chain rule of forecasting. All this will talk about is you forecast for the next period. So you set up your model and then you say, okay, what are sales going to be next period? Or what is inflation going to be in the next period? What about the period after that? 2 periods later. Then we'll use the chain rule. And then comparing forecast model performance. If you are evaluating 2 different models and you need to pick the better one, how do you figure out which one is better? And finally, we'll talk about the instability of regression coefficients, which means that under certain circumstances, the regression coefficients might change. All right, 4.1 covariance stationary series. For AR models to work, the time series must be covariance stationary. We touched on this in the previous reading. Now let's just look at the 3 specific requirements for time series to be covariance stationary. The first one is that the expected value of the time series must be constant and finite in all periods. Remember this. If you have a situation like this, where over time the value is slowly drifting upwards, is this covariance stationary? No, because the mean is changing. So this is the requirement. The second is that the variance must be constant. If you have a situation where the mean is not changing, but the variance is changing, then this is also not stationary. And then finally, the tougher one, and one I'd say you just remember, is that the covariance of the time series, past or future, must be constant. So if you look at the covariance between terms, that should also be stationary. You can't have a situation where the covariance between terms over here is low, and then over here the covariance between terms becomes high. That is a little hard to show graphically, but I'd just say you remember that the covariance between terms should also remain constant. This doesn't mean that there shouldn't be covariance. It simply means that the covariance should not change. All right, section 4.2, detecting serially correlated errors in an autoregressive model. So this is a common theme. How do you detect this? Very testable and something that you need to just memorize. The Durbin-Watson statistic does not work for AR models. The way you can think about it is the Durbin-Watson statistic only works when the dependent variable and independent variables are different. Did Durbin-Watson work for time series where we are looking at a trend? So time was the x variable. There it worked. Did Durbin-Watson work in the previous reading where we had y and then x1, x2, etc.? It did. But when you have AR models, then DW does not work. Okay, so keep that in mind. Even though when you get your regression output, does the regression software know that you are doing a time series? Not necessarily. So when you look at the output in this section, you will see DW. But what do you do with it? Ignore it. So what do we do to test whether there is autocorrelation? Test whether the autocorrelation of the error term, this is also called error autocorrelation, differs significantly from 0. And let me explain how this works and what this means. Let's take a simple situation. So let's say you run an AR model, and for now we'll say that you are regressing X with a previous version of X. And you have, let's say this is your actual data. I'm just making something up. And then this is the regression line. What you do is you look at the various error terms. What is the first error term? The first error term is this amount. What is the second error term? It's this amount. Then let me just put the third one over here. This is the third error term. Ignore that. This is the fourth error term. Let's say that this is your fifth error term and this is your sixth error term. The moment you run a regression, do you know the error terms? You do, because you have your data, the actual data, you have the regression line, so you know all your error terms. If you've really understood this concept of error correlation, then what I'm going to say next will make a lot of sense. What you now do is run a regression of the error terms. So what you do is this. You run another regression now. So this was regression number 1, based on which you came up with the error terms. You run another regression, and let's just call it a lag 1 regression for now. And what do you do in a lag 1 regression? You have a X and a Y. And a simple way of looking at it is you regress error terms against the error term 1 period earlier. So if this is your data, the second error term versus the first error term, the third versus the second, the fourth versus the third. So you run this regression now. You get 2, 3, 4 in one column, and then the parallel column will be 1, 2, 3, and tell your software to run a regression. This is called a lag 1 regression because you are regressing each error term with one lag earlier error term. Now, when you run this regression, will you get an equation? You will. You will get an equation as usual in the form y is equal to b0 plus b1 into x, where the y and the x are simply the error terms, and the error term in this case would be one lag previously. Now, if based on this you get the b1, and then you look at the test stats associated with b1, and you conclude that b1 is statistically equal to 0. In other words, to be more precise, you cannot reject the null hypothesis that b1 is equal to 0. Would that be a good sign or a bad sign? What do you want b1 to be? You actually want it to be 0. So you want a situation where the null hypothesis is not rejected, because if b1 is equal to, let's say, 0.5, and based on the t-stats you cannot reject the null hypothesis that b1 is 0, then you have a problem. You have a autocorrelation problem. Okay, now is it sufficient to say that you just lag with one error before, Or should you also do a lag 2 and then a lag 3 and a lag 4? You should. How would a lag 2 work? Here you would look at the third error term versus 1, the fourth error term versus 2, and so on. This would be a lag 2. And then again you run the regression and see whether you can reject the null hypothesis of B1 being 0, and so on. The rule of thumb is to do this up to at least 12 lags if you are looking at monthly data, and 4 lags if you are looking at quarterly data. Let's now look at example 4, where we will apply the concept that we have just learned. In this example, we are predicting gross margins for Intel. And what I want you to do first of all is look at the regression statistics and tell me whether we have an AR1 model, AR2 model, or some other AR model.
AR1.
We have an AR1 model because we only have one lag. So this data over here, section 1 and section 2 of this regression output, refers to the AR regression, where you are regressing the gross profit margin in a given period against the same variable one period earlier. Whenever we do an AR regression, we get our numbers. So do the numbers look good? R squared looks decent. We have coefficients. The t-stats are pretty high. The rule of thumb is to compare the t-stats with 2. And both of these are above 2, especially the lag one. So it looks like Intel's profit margin in a given period is heavily dependent on the profit margin in the previous period. Business-wise, that also makes sense. You would not expect to have a situation where profit margins vary a lot from period to period. The next thing though is to check whether we have any autocorrelation issue. And that is given over here. Whenever you see this autocorrelation of the residual, so these are now additional regressions. So what does lag 1 mean? Here we are lagging. So what does lag 1 mean? What we are doing here is regressing an error term with one previous. In that case, when we do that, what do you think this 0.0677 means? What it means is, in the regression, this is the B1 term. This is the term that is connecting an error term with one period earlier. What do you want this to be? You want this to be 0. So what is your null hypothesis? Your null hypothesis is that B1 is 0. That's the null hypothesis. The null hypothesis always needs to have a equal to sign. Okay. Can you reject this null hypothesis? What you do is you look at the test stat. The test stat is pretty small. It is much less than 2. So you cannot reject the null hypothesis. What about when you do the lag 2? Here error terms are being regressed against error terms 2 period before. Here the error terms are being regressed against errors 2 periods before. What is the null hypothesis? It's still the same. H naught, that B1 is equal to 0. The t-stat is still much lower than 2, absolute value wise. In fact, all these test stats are much lower than 2. Okay, so that means that, at least statistically speaking, we do not have a autocorrelation issue. Why do we go to 4 lags? I did not explicitly mention this, but we are looking at quarterly data. Generally, when companies report, they report every quarter. So you are an analyst, you are looking at quarterly gross margins for Intel. So with quarterly data, it is okay to look back 4 lags. All right, a few more points before I move on. Something I did not mention on the previous slide, this concept of the standard error. The value of the standard error, notice, is always the same. And from an exam perspective, just remember this formula. You don't need to know how to derive this. The standard error is 1 over root t. And the reason I accidentally said n is, in a way, this is an n. T stands for the number of periods. So in our case, it is the number of observations. So if we do this, 1 over square root of t, what's t? In this case, it is 59. So you do that and you should get this particular number. So you can do the maths and see that the standard error when you do 1 over root of 59 does come to be this number. What is the formula for the t-stat? The t-stat is equal to this number, the estimate 0.0677 minus the hypothesized value, which is 0, divided by the standard error, which is 0.1302, and you will get this answer, which is 0.5197. The regression output is given. So you really don't need to do these calculations. But if I were an examiner, then I might leave this blank. Just by knowing the number of observations, we can come up with the standard error. And if we know this number, we can come up with the t-stat. So it is quite easy for them not to give you this data, and then you figure out the t-stat, and then you figure out whether there is an autocorrelation issue or not. Okay, so that's pretty powerful. Now you might be wondering, if you still remember your level 1 material, that generally you want to reject the null so as to move towards the alternate. That is the typical thing to happen, but at level 2 you realize that there are some situations where that doesn't necessarily happen. So in this case, for example, you go with the other more fundamental rule that the null hypothesis must have an equal to in it. That rule overrides. So the other one, so that is the rule of hypothesis testing. The other one, which says that you generally want to reject the null, that is something that is a guideline. That's one way of looking at it. The other somewhat silly way of looking at it, but it will help you remember, is that this regression has been done by your colleague, and you actually want to show your colleague that he has done something wrong. So you want to poke holes and you want to find a problem. If that helps you remember, well and good, otherwise we move on. Let me go back to the previous slide for a moment now. This set of sub-bullets will make sense. When we look at the lagged error terms and we are running that regression, what's the null hypothesis? It's that the error autocorrelation at a specified lag equals 0. What do we mean by specified lag? It means first we look at lag 1, then lag 2, then lag 3, and so on. So each one, in each case, the null hypothesis is that our coefficient, the B1, equals 0. What is the standard error? This is the formula, 1 over root t, where t is the number of observations or the number of time periods that you are looking at. And then what is the test stat? It's the residual autocorrelation minus 0. So for simplicity, I've just said the autocorrelation divided by the standard error. I've done example 4 with you. What you need to do is example 6, which is very similar. Obviously, you really understand this material when you do it yourself. We now move on to mean reversion. A time series shows mean reversion if it tends to fall when its level is above its mean and rise when it is below its mean. So what does this mean? If you take inflation numbers, for example, in a given economy, there will be over time some average number for inflation, hopefully, right? In some countries, it seems that inflation keeps rising, but let's take developed countries. There might be some mean level. And if inflation is particularly high at a given point in time, you would expect inflation numbers to come down. If inflation numbers are very low at some point, you would expect them to revert towards the mean. We then say that this particular variable has mean reversion. If you consider an AR1 model, and let's take this AR1 model, so you have a given variable at time t is b0 plus b1 times the variable one period earlier. The formula for this mean reversion level is given right here, and you must memorize this because we will use this formula later. If I have this particular AR model where xt is equal to 0.5 plus 0.25 times xt minus 1 plus the error term, what is the mean reversion level for xt? This is actually the mean reversion level. I should say mean reversion level for xt is going to be 0.5 divided by 1 minus 0.25. So you can do the maths, and that is your mean reversion level. Again, I'll emphasize, just remember this because we will use this formula later on. Section 4.4, multiple forecasts and the chain rule of forecasting. Say you want to forecast for more than one period. So you want to know the result in the next period. So predict the next period and then predict for the period after that. What do? You use the chain rule. And what is the chain rule of forecasting? The chain rule of forecasting is a process in which the next period's value predicted by the forecasting equation is substituted into the equation to give a predicted value 2 periods ahead. This is fairly straightforward. If this is your equation, is this a forecasting equation? We've not called it this before, but that's what we have. We are not doing all this for fun. We are doing this so that we can forecast, right? So, which might be fun for some people. So x is equal to b0 plus b1 times x at time t. If you know x at time t, so if this is known, and you run the regression which gives you b0 and b1, then can you figure out x at t plus 1? That is a forecast. What do you do next? In the same model, then you plug in xt plus 1 to get xt plus 2. Fairly straightforward. The fact that you first came up with this and then came up with this makes it look a bit like a chain, and hence this is called a chain rule. Example 5 is a short and sweet example which illustrates the chain rule. I'll actually just have you go through this, but you ran the regression. So with a given value of x, you can predict x in the next period, and then that next period is plugged into the same equation to predict 2 periods out. Okay, fairly straightforward. I'm sure you can read this and understand what's going on. Moving on. Comparing forecast model performance. The basic idea is that you have multiple forecast models. Let's say you have a model A and a model B. Which one is better? One way to compare the forecast performance of two models is to compare the variance of the forecast errors that the two models make. The model with the smaller forecast error variance will be the more accurate model, and it will also have the smaller standard error of the time series regression. So fairly straightforward. The model with the lower variance and the lower error is better. If you read through example 7, this will be illustrated quite well. So I will want you to do that. The other important point is to distinguish between in-sample forecast errors and out-of-sample forecast errors. The point being that you've created these two models A and B, and both these models were created based on some data. When you create a regression line based on this data, and then you look at the errors, where you are looking at the forecasted value relative to this sample data, then the regression output, the forecast error variance and the errors, that would be called in-sample forecast errors, because you are comparing the regression output with this sample data. Then you take the regression model that you have, which is effectively your equation, and apply to some other data. So that is out of sample data. The real value of regression is if it works in out of sample data, because in sample data you have anyway. So the best that the regression model will do for you with in sample data is some form of interpolation, right, with that data. But the real value is with out of sample data. So just because you come up with these forecast error variance numbers and standard error numbers here, you also need to look at some metrics with out of sample data. All right, you can't just say that A is better because it has better numbers with in sample data. So you should compare the out of sample forecasting performance of forecasting models by comparing their root mean square error. And this term actually is explained by the name. What is it? Which is the square root of the average squared error. And I'm going to show you example 8, which does this calculation. I doubt that you will be required to do this calculation in the exam, but it is mentioned in the learning objectives. So I would say that you need to understand what this is all about. Okay. Let's say we want to compare the forecasting accuracy of two models. One is an AR1 model and the other is an AR2 model. And the underlying data is US inflation estimated between 1971 and 2000. All right, so we have the data. What I've done here is reproduced an excerpt from the curriculum. So we have all the data for 2001, and then we also have monthly data for 2002. In any given period, this is the actual inflation number. In this column, we have the error associated with the AR1 model. In this column, we have the error associated with the AR2. So let's just look at the AR1 model first. So this is the error, then this is the squared error. The squared error for which model? For the AR1 model. So we compute all the squared errors. And why are we squaring? Because if we don't square, then the plus minus will cancel each other out and we won't have a meaningful result. So obviously we square. And then what do? We then take the average. What is this thing called? It's called a root mean square error. So you take all the squared errors and then you take the average and then you take the square root of that average. So this is the metric. This is the number that tells us how good the AR1 model is. But to be precise, you can't just look at this number in isolation. You are comparing. You do the same thing with the AR2. So over here we have the AR2 model, and you come up using the same process with a different number. Given this information, which model is better, the AR1 model or the AR2 model? The AR1 model is better. The moment you are looking at something related to error, so this RMSE, root mean square error, is an error. So you want that number to be lower. So anytime you are comparing two models based on the error or based on the variance, then the lower number is better. So based on this, based on the outer sample analysis, AR1 is slightly better. Okay, there might be other metrics you also look at, but here you've understood RMSE. And again, I'll emphasize, the calculation is not very hard, so I don't think you'll be made to do a lot of calculation, but you need to understand the concept. Moving on. Instability of regression coefficients. What does instability mean? It's a fancy term. It means changing. So if you set up a regression equation, you have B0, B1. Is there a guarantee that these numbers will not change? No. Estimates of regression coefficients of the time series model can change substantially across different sample periods used for estimating the model. When we select a time period, we need to keep the following in mind. Determine whether the economics or the environment have changed. So for example, if you take an economy like India's, at some point the economy opened up, or you take the Chinese economy. So at some point there were fundamental changes in those economies. So if you are running regression of interest rate numbers or inflation numbers, it makes sense to consider the fact that there was a regime change. A regime change in this context doesn't mean a political regime, it means the fundamental economics of the situation changed. So if you are running a regression which spans multiple regimes, then you are going to have a problem, because typically the regression coefficients will change from regime to regime. Now, how do you know that a regime is changing? The simplest thing to do is look at the graphs of the data to see whether the time series looks stationary. If your interest rates look stationary, then it seems that would be an indication that there isn't a regime change. In other scenarios, if you notice substantial changes, this looks like there is a bump up, then that would imply that there is a regime change. So example 9 talks about the fact that between 1971 and 2000 in the United States, we actually have two regimes, one from 1971 to 1984, and then another from 1985 onwards. Why? Because there was probably some major policy change in the early 80s, because of which we have two different regimes. You don't need to understand the details of what happened, but just recognize the fact that there might be a regime change.